Welcome back. In this lecture video, we now get into the next module on stratified random sampling. Now, the goal of sampling is to select observations from a population in such a way that as much information as possible is obtained from the population for a given cost. Stated in statistical terms, we want our estimators to have as much precision as possible and our hypothesis test to be as powerful as possible. Accomplishing these goals depends on two things. First, using the correct estimators for a given sampling framework, and two, sampling the population in such a way that estimators exhibit as little variation as possible. Stratified random sampling can provide more information per observation from a population than simple random sampling when the population consists of two or more well-defined strata based on characteristics that can affect the outcome measure of interest. Stratifying is effective when the outcome measure of interest tends to be similar within strata, but different between strata. When this is the case, estimators can exhibit greater precision when stratified random sampling is used than if simple random sampling had been used. Now consider a finite population consisting of a number of strata, which we will denote by cap L. For each stratum, j going from 1 up to cap L, let cap n sub j denote the number of sampling units within stratum j. Denote the total number of sampling units in the population by cap n. Then clearly cap n is going to be the sum of the number of sampling units within the various strata. Now let's look at some notation that we'll use to denote the members of the population, and in particular the members of each stratum. So we're going to denote the ith member of the jth population stratum by u sum ij. All right, so with this notation, the population can then be listed in the following way. Notice that we have a set here. It's really a set of sets. And so we have the first stratum consisting of the members u11, u21, and so forth up to u sub cap n1, comma 1. The members of stratum 2 would be denoted u12, u22, and so forth up to u sub cap n sub 2, comma 2. And finally up to the last or lth stratum, u1l, u2l, and so forth up to the last member in that stratum, u sub cap n sub l, comma l. So in this notation, the second subscript is the stratum number. The first subscript is the member within that particular stratum. Next, we will denote the stratum totals. Denote by tau sub j the total of stratum j, j going from 1 up to cap L. So tau 1 is the total of stratum 1, tau 2 is the total of stratum 2, and so forth up to tau sub L being the total of stratum L. And you can see here that we are just representing these or calculating these stratum totals by summing up the appropriate members from the various strata. Now we will denote the stratum means, and so denote by mu sub j the mean of stratum j, again j going from 1 up to cap L. So mu sub 1 is the mean of stratum 1, and this can be calculated in a couple ways. It can be calculated as the total of stratum 1 divided by the size of stratum 1. All right, so in terms of it can be expressed in terms of tau and cap n, tau sub 1 and cap n sub 1, or we could represent it this way, 1 over cap n sub 1 times the sum I going from 1 to cap n sub 1 of u sub I1. Similarly, the mean of stratum 2, which will be denoted by mu sub 2, can be represented in terms of either the stratum total and the stratum size, or in terms of the individual members within that stratum, their sum divided by the size of that stratum, and so forth down to the last stratum. So again, we have the notation here for the stratum means, mu1, mu2, and so forth up to mu sub cap L. And these can be expressed either in terms of the stratum totals or the individual stratum members. Now notice that once we have this representation for the stratum means, then we can go back and we can re-represent the stratum totals in terms of the stratum means, where tau sub j is equal to cap n sub j times mu sub j. Now, denote the variance of population stratum j by sigma squared sub j. Then the stratum variances are given by the expressions on this slide. And so you can see here that these are just the formulas. These are population variance formulas, but applied to the various strata. All right, so sigma 1 squared is the variance of stratum 1. Sigma 2 squared is the variance within stratum 2, and so forth up to sigma squared sub L, which is the variance within stratum L. Now the overall population total, which we will denote by tau without a subscript, can be represented in a number of ways. First, it can be represented as the sum over the entire population of members, so across all strata, of the members within each of the strata. So the sum j going from 1 up to cap L, and then I, for a given j, I going from 1 up to n sub j. All right, and what are we adding up? We're adding up the use of ij's, so the members, the values associated with the members in each of the strata. We could also represent the population total as the sum of the stratum totals. And then finally, given the representation of the stratum totals that we looked at before, where that is equal to the stratum size times the stratum mean, we could represent the overall population total as this weighted sum of the stratum means, where the weights are the stratum sizes. The overall population mean, which we will denote by lowercase Greek letter mu without any kind of a subscript, can also be represented in several useful ways. We can represent it as the ratio of the population total to the population size. All right, and we can also represent it in these other ways as well. All right, and each of these ways will come in handy at some point, and so that's why we give the three representations here. Once we have this expression for this first expression in particular, for the population mean, we can go back and re-express the population total in terms of the population size and the population mean, right? Tau being equal to cap n times mu. So now that we have all that notation defined and the formulas defined for the various characteristics of the population strata and the population overall, we can talk about the stratified random sampling process in particular. And so how do we go about performing or selecting a stratified random sample? Well, the first thing that we need to do is to make sure that the strata are specified. So we have to specify the strata, and the strata must be mutually exclusive and collectively exhaustive. And what that means is that there's no overlap between the various strata, and that if we put the strata together, we get the entire population. Another way to say that is that every member in the population belongs to one and only one stratum, okay? Once we have the strata identified, then we have to, or specified, then we have to identify the stratum that each member of the population belongs to. Once we've done that, then we select a simple random sample from each stratum. Now the samples must be selected in such a way that they are independent of one another. So samples from different strata must be independent of each other. That is, the observations chosen from one stratum must not depend on nor influence the selection of observations from any other stratum.